So the title of the talk is Algebird and Unification. The unification in this case refers to like unifying several different libraries, not some crazy like type unification or anything like that. So if you're like already freaked out about too many M words, like there'll be not too many scary M words here. So also I'm at Stripe now. Algebird, of course, was developed while I was at Twitter, where we had to name everything contractually after birds. Don't know what to do really now, but we're still thinking about it. So the first part of the talk is going to come in three parts. First, I'm going to talk a little bit about algebra. So here we go. If you haven't done anything but like addition in the past, you're probably fine. So here's like the main thing that like, so my background is mostly dealing with data. So dealing with, machine learning. I'm on the machine learning infrastructure team at Stripe now. So we're dealing a lot of times with building features that we want to use to make predictions. And sadly, as much as it sounds all fancy, usually that's just like counting and adding things up. So like grouping, like word count, right? You've seen it a million times. And the cool thing that I noticed there at Twitter years ago, that like some really interesting things had the property that addition has. That this is a really useful property, it's associativity. So it doesn't matter whether or not if I'm adding 1 plus 2 plus 3, if I first add 3 or to 2, or if I go 1 plus 2. I'm gonna get the same result in the end, 6, right? So this is called associativity. It's one of the most important properties that we're interested in these like algebra libraries. And it just means that you can put those parentheses wherever you like. You probably know other things that have that structure. So like, string concatenation also has that structure. So I can add either, hey you, and then add 2 on the end, or I can, push, u to 2 and then add hey on the front. So it doesn't really matter. So the lesson there is that like you can put the parentheses wherever you want. That's a really cool property. So this actually comes up all the time. So this is given a name. So really, people talk about monoids a lot. Actually, when you're dealing with data, you always have one of them. So you actually don't need that zero quite as much. So the semigroup is a thing that really has this first property. You might think like semi-monoid might have been a better name for it, but algebra has a long history. So it's called semigroup anyways. And one cool thing, once you have a semigroup, if you're dealing with distributed computing, is that you can, you can do a parallelism. The commutativity that you might want to think about, it has an application, but just the semigroup alone, just the associativity gives you the ability to do parallelism. Because you can break this expression up into a tree, and then you can, let's see, we've got a latency here of like 4 combined operations at maximal parallelism. So that's the cool thing. That's why you should be pumped about associativity. So when you're dealing with some objects, some data objects, and you're putting them together, and you want to do like trillions of them, like associativity is a really nice property to have for that reason. So it comes up super often when you're dealing with like really concrete things. So this is a pretty simple abstraction. Like if you were just at the Matryoshka talk, like we're not going to get anywhere near like holomorphisms or catamorphisms or anamorphisms. This is pretty straightforward stuff that you can wrap your mind around. So like max, or integer addition. You can think of a lot of these. Set union, set intersection. You can really spend a lot of time. And this is a really weird one. It actually comes up in like one case, which I'll just point to. Like even harmonic sums turn out to form a semigroup. They're associative, even that weird formula there. And then you can compose. So if you have products, like tuples, case classes, if each of the thing in the product has a semigroup, then the product has a semigroup. So that kind of standard composition, so you can kind of go all day with that. So like one cool thing is like a Bloom filter. So here's something a little bit non-trivial, and these are the kinds of things that we are interested in the Algebird library, is like kind of interesting data structures that have this kind of property that we can kind of combine them in a nice way. So a Bloom filter, I like to say it's like an approximate set. It's something that can tell you membership like with some probability. It can say, this is definitely not a member of the set, or it may be a member of the set. That's the kind of approximate part of the Bloom filter. So the way that the Bloom filter works is it's just a product again. And remember that products like already have this kind of nice, like if you have a semigroup and we take two things and glue them together, you can still make a semigroup. So you've got a product of bits or Boolean values. And then when I want to kind of merge things in, I use this OR operation. So I have a new item here, I comes in, I hash it a few times, and I produce a new very sparse vector. So this is a super sparse vector of like all zeros and like 3 ones. And I combine it with my existing vector by doing a bitwise OR. So that whole process, everything I've just described, they were still semigroups, right? OR is a semigroup, the products are a semigroup. So the Bloom filter is a semigroup. So I can go through and in parallel produce, Bloom filters, no problem. Yeah, I can add more to it and whatever. So to read from this thing, interestingly, you check, so to write into it, you do one semigroup, or a monoid. In this case, it's a monoid too, but we don't really care so much. You do OR, right? You go through and you OR these things in. To read from it, to check if something's there, you actually, interestingly, and this is like a little, bit of trivia almost, I haven't really seen how far you can push this generalization, but you use a different semigroup, which is AND. If you want to read from the Bloom filter, for instance, if I want to read to check J, is it present, I read each of these, I produce the sparse vector for J, and then I go through and I AND one with this, one with that, all of them together, and if that returns true, then I think it may be a member. So there's two different semigroups at play if you want to understand Bloom filters. So there we go. Man, sorry for the autocorrect. I probably corrected it like 4 times. I don't know what a monodies is, but it kept wanting to convert it to Moonies or something, or Moody's or whatever. So this structure came up several times, and it was really interesting. So in Algebird, you can use these. One, you get the data structures, but 2, you get them in a way that you can compose them in a really nice manner. So I've talked about Bloom filter. 2 more approximate data structures which are really interesting are hyperlog log. It's another approximate set. Bloom filter is mostly talking about set membership, though you can use it for counting size of a set. Hyperlog log is really focused on an approximate estimation of the size of a set. So if you have, say, Twitter wants to count how many unique users they have, and it's a it could be, they know the maximum user ID they've allocated, but because not everybody maybe is active in a particular month, that's not the number of users they actually have, so they want to go through all the data and see how many people have logged in each month. So if they just made a giant vector of 100 billion or something, because that's like all the IDs, that would be really inefficient, and only say around 300 million or so of those bits will be 1, right? Instead, with hyperlog log, they can make a really compact data structure, like around 10 kilobytes or so, and get a very accurate estimate of the number of unique users that were present. That's pretty cool, and the way that works is by basically doing a product of using a max. A bit about, like we saw in Bloom filter, you do a product of ORs. Hyperlog log winds up being a product of maxes, and you read from it using another monoid, which is like a weird curiosity, this harmonic sum, which turns out to be a monoid. That's really cool. Count-min sketch is a way of doing, I don't want to see how many unique items I have, I want to get an approximate count. So I want to know how many times each user came to the site. I don't really care how many unique users. So I want to produce a data structure, and then you can ask me a question, and I can kind of query it and see, well, it looks like, Sarah showed up, 14 times plus or minus, whatever. I can use some error bars. That's also a monoid. So anyway, so these are the kind of things we got interested in. That's what you can use Algebird for. We got many others. Qtree is an approximate histogram. It's also forms a nice associative. It's actually a monoid structure. Average value. If you have 2 numbers and you want to know the average, well, the sum is clearly your kind of knee-jerk reach for it example of a semigroup, right? For like I put up on the first slide, 1 plus 2 plus 3, right? But the average value also, clearly that would be associative as well, because I could just keep a side count of well, I've seen one thing and here's x. I've seen another thing, and here's x2. So I could clearly put them together, but the nice thing, there's actually stable algorithms for computing the average that are numerically more stable than just summing up and then dividing. That's going to get you into trouble with overflow in some cases, and there's some other properties about it that you don't like. So even the nice stable algorithm forms a monoid, which is pretty cool. Decayed value, I love this one, this exponential moving average. It happens to be that the exponential moving average, which is something that's weighting over time, you've probably seen it in stock charts or something like this. These can be combined associatively and commutatively. So there's a lot of really nice stuff. Top K applications, I want to see the most frequent domains that refer to my website. That's a top K application. They can also be built in this way. So this algebraic framework, I'm more of a math background than computer science, category theory. So I hear some people kind of lump them together. I don't really think of them so much that way. These very algebraic kind of concrete abstractions have a lot of applications in data, prediction, ML, etc. So that's Algebird gives you these. You can use them pretty easily with Spark, with Scalding, and that's pretty cool. But what more can we do? So that's part one. Are there any questions at this stage? I've talked about some of these things before, so I kind of wanted to just give you can find a lot of other talks and other people talking about these things in detail on the web. But we're going to move on now to a little bit of the category theory I was just trying to badmouth and kind of side-eye a second ago. So. All right, let's do it. So, well, we have all these semigroups and monoids. And people talk about these. Everyone loves the monad, and you can't go to a talk here without hearing one of these abstractions. So one interesting abstraction that came up, which follows a pattern called applicative, which we'll see, is this notion of how do I go from my type that I really care about to this type I talked about. So I was talking about hyperlog logs. Well, your access logs don't have hyperlog logs in them. I was tripping over the fact that log appeared in that access log and hyperlog log, so that was a bad example. But so your access logs don't have Bloom filters in them, right? They've got user IDs. So that's a bummer. So you've got to convert somehow from your access logs, which maybe have some user ID, to some Bloom filter or some countmin sketch. So over here you're talking about, oh, there's this cool thing, but you don't have those things. You've got numbers or strings. So how do we do this? So this is Bootsy Collins from the legendary band Funkadelic, We Want the Funk. So you got to have the applicative functor here at this point in time. So how would we calculate the list, the size of a list if you were constrained to MapReduce? So if you go and join a company and you're working in machine learning or analytics, you can compute anything with MapReduce. Your whole life is just writing all algorithms as MapReduce. So how do you do it? Well, you first map everything over to 1, and then you reduce. That's all you've got. You got map and reduce. So it turns out the length of this list is 7, and we had our nice associative structures, so we can do parallelism in 2 phases. Here we have total parallelism, trivial parallelism, and the associativity still gives us parallelism on the other side. So everything's awesome, super fast, we can scale it, life is good. That's why MapReduce is so awesome, because you can separate this system kind of question of how do we parallelize from the logic in a very, very clean way. It's I'll give you this MapReduce abstraction, you go to town logically, but the systems folks can still optimize the hell out of it. And that's the power of any great abstraction. So we've got the semigroup, that showed up, but what we really wanted in this case was a map plus a semigroup. We want to glue it together, because I wanted to have this one function of length, right? So length is not a semigroup. Length is 2 things. It's map plus this semigroup, okay? So what if I want the average of these numbers, though? If I wanted the average of these numbers in a naive way, I could maybe map each number to the count 1 plus itself, identity function. So 1 and 2, 1 and 3, 1 and 5, etc., right? Now I can go reduce them all together using a pointwise addition, and I get 7 items, and the total sum is 58. But I'm still not at the average yet. I've got some weird tuple, and no one wants that tuple. They want the average, right? Ain't nobody got time for that. So at the end, I'm going to like just divide, convert it to a double. Okay, great. So what I really want is an abstraction that's like map plus a semigroup plus a map glued on the end. And so we're not trying to be too highfalutin. We just call this aggregator. In the Haskell world, it turns out coincidentally, we did not know when we saw this, but like, good abstractions have been discovered like 1,000 times each. They call this fold M. But we call this an aggregator. So this aggregator has like a function that comes in the front. We call this prepare, again, because we've got to sell it to people who don't really want to hear about catamorphisms and anamorphisms all day sometimes, unfortunately, but hopefully we can sell them on that too. We do our semigroup, and then we do a present function that converts at the final at the end. So what's so cool about this? Well, one cool thing is that you can start to write calculations that look a lot more like SQL, because a lot of SQL is actually kind of already encapsulating these kinds of things. So here's like an example of some table. I've got some order IDs up here. This is like standard business logic. It makes us all legitimate and validates our interest in functional programming. So the SQL is just like, okay, I want to select the count from the orders. And then once you have these aggregators, you can kind of glue up in one abstraction a lot of your computation. So here's like the Scalding representation, but the Spark is pretty much the same. That you say, let me get the size aggregator from, we got several of them predefined, and then just from my like typed pipe is like basically RDD or like a distributed list if you like. Just aggregate it, give me the size. Boom, I've got the size. What if I want to do the count where the customer name is Smith, right? Well, I can take the count aggregator and say count this predicate. So count where customer name equals Smith, and boom. So the count also fits into this model of being an aggregator, which has this map, semigroup map structure. And you can, group by. So in this case, we're going to group by whatever. That's not so particular to the aggregator construct, but you can keep going with this. You can really take it a long ways. So why should you be excited about this? So what's the cool thing about this? So the cool thing was Bootsy Collins playing the bass, talking about applicative functors, right? So that's the cool thing. So once we have this is a little picture that I can draw of what the aggregator looks like. You've got your map, your reduce, and your present, right? The cool thing is, well, as my former colleague Dan Rosen says, does not compose is the new, quote, is a piece of crap. So, and aggregators compose. So that's awesome. So how do they compose? So we can glue another function on the front and I still have an aggregator, right? Well, functions compose. So since I can compose a function on the front, I can still get an aggregator. So I, like, in a really silly kind of like a pseudo mathematical way, a function glued onto the front of an aggregator is still an aggregator. So it composes that way. If I glue a function on the tail end of it, by the way, quiz time, get everybody talking. What do we call this, like in more of a category theory? Like this is, yeah, it's contravariant function. And the first, it's contramap, yeah, so cool. We can glue a function on the end of it and we've still got an aggregator, no problem there, right? Because like these things are yellow. I can just glue them together, like no problem, So that's called map. Things that we can glue a function on the end of it, we still have that thing. We call those functors. But more than that, I could kind of like glue them together product-wise. I could have like first been pulling into one, then into the other at the same time, and then output something else. I like this representation of applicative functors. Sometimes people call these monoidal, I don't really think that should be a word, but monoidal functors. But anyways, I can kind of like glue them together. So the zipping kind of thing, like you can kind of zip two lists together, or you can kind of join two futures together where you have a future of A, a future of B, and glue them together. Like you have that zip operation, that's the applicative functor with some other stuff and some other laws. So we've got that. So aggregators are these applicative functors, so which is pretty cool. So we've got a map method, that's the thing on the end. We've got this zip method. We do not have the flat map. So there's no great way to make, and there's some nice reasons why monads are just too much. You know, you're just going, just take it back a step. And there are really nice things about applicative functors, so that's pretty cool. Cool. So that's the story with aggregators and applicative functors. So you can use this with the Algebra project has the Algebird Spark. You can just kind of like grab that thing off Maven. You can pretty much take your RDD and aggregate and use all these nice abstractions. So that's cool. So if you're using Scalding, they're kind of built in. It's like this was really pulled out of Scalding to make it more portable and to be able to use it in more contexts. Any questions about that? Yeah.
So the 2 slides ago, so when you compose those aggregators, right? So they have to be in the same shape, right? Same cardinality.
Yes, I will repeat the question. The question was, when you want to compose these aggregators, and I apologize a little bit, I've decided, I didn't show so much code as I just kind of talk about concepts, so this would be easier to talk about if I put the code up. If I compose these 2 aggregators, they have to be of the same shape. So you want to, there's actually 2 ways to compose these things that look pretty similar to zipping them together. One would be, and I wish I had a chalkboard or something. What? Maybe, yeah, I think I've got time. So I'm just going to like come over here to a text editor. So let me increase the font size. Okay, so one of them is you have aggregator ABC and aggregator, let's see, def, like combine, right? Okay. And you also, over here you have aggregator or A1, B1, C1. Okay, so I can compose these into something like this that's aggregator A1. That's one way to compose them. This is not exactly what we mean generally when we say an applicative functor. So I'm just kind of like, I can like do this at the same time. So if you were to bring me a list that had A and A1, I could just like yank one out and put it through one and one out and put it through the other and go through. So that's one way to compose. Let's combine sounds bad because it sounds like something else. So I'm going to say compose 1. Another way to compose is this. So they compose in many ways, I guess is the answer that I'm going for, but I'm just going to be concrete about the 2 ways that they compose that are most interesting. This is maybe the more interesting way, that if you bring me a list of A, I can, and this is the one that looks more like the, this is the one that you would implement an actual applicative for in CATS or Scala Z, that second composition. Was that question, was that a reasonable answer to that question? Okay. Okay, so that's that part of the story. So what's the whole unification part of the story? So a couple years ago, so here's the part 3. Here comes part 3. So like everybody's got a monoid. Like I think every single talk I've been to in this conference, they've mentioned the word monoid. And like it takes you like literally it's like 4 lines of code with the parentheses and everything. So it's like that's not like some big contribution to the world, So, here's like Algebird's monoid, and you've got Spire's got a monoid up there, and Scala Z has a monoid. And like actually, there's 8,995 just Scala hits to monoid on GitHub. So like that's that's like a bummer, man. It's like there's just too many of these things, So and it's been slow going. I remember it was almost like 3 years ago. Like I was thinking like this is a bummer. Eric Osheim, who I work with now at Stripe, he's like, yeah, we shouldn't do that. We should have one thing. And we were like, yeah, Miles, what do you think? I don't know if Miles remembers us asking. He was like, No, it's not a bummer. Just like, you know, like have implicit conversions between the ones you want. You don't need to have one big monoid to rule them all. But, you know, so anyways, but then, you know, later we decided, like, let's give this a try. So we had this algebra project, okay? So the idea of algebra was, now we're going to veer off into like history of like Scala community. At this time, like there was this guy Lars who was running this project called Scala Z. And so Lars and like Scala Z and like Eric with Spire and, you know, Avi and I with Algebird, we had this like video thing. We were going to like get together. We're going to have one set of these basic abstractions that are just so simple. You just can't like, you're not going to get them wrong. Like you're going to agree to them and they could really be kind of hopefully frozen. And the algebra ones really kind of feel that way. So that was the kind of goal. We kind of probably dragged our feet on this because there's also one problem in the Scala community. If you're working at a big company that has a large code base, you start to become very anxious about binary incompatibilities. And I'm sure everyone has been bit by diamond dependencies of like very commonly used libraries. So a library such as this, which you're proposing to put it's like the XKCD thing. It's like there's too many standards, so I've got it. Like one more standard, right? And not only that, you're going to jam it at the very bottom. Like let's jam it underneath Spire. Let's jam it underneath like one of our core algebra libraries at Twitter. Let's jam it underneath Scala Z. So it took us a long, we wanted to be really sure we'd kind of gotten it right before we jam it in. And then like, I think really before Mima was so much of a thing, but so now there's Mima, a tool to help you like at least know when you've broken binary compatibility, which unfortunately is not perfect. So anyway, so that's the story, but we dragged our feet too long, and then Miles again, causing problems, was like, look, like you guys, that was fine, but like I'm just going to need to take like those things and take a copy and put them in type level. We should just do that in the type level cats thing. So we then we did that. So let's see where we got. So these were the main abstractions that were most commonly used. So we've talked about semigroup and monoid today, and I've talked a lot about what associativity means. The rest of these maybe are like, they're simpler properties, certainly simpler to check. Commutativity just means, or commutative, it just means if it's A and B combined, it's same as B and A. Identity means you've got some element that I can combine that doesn't do anything. Inverse means that I can uncombine. So if I've combined in like A, I can also uncombine and get back where I was before, right? And idempotent, which is super useful for the distributed system folks out there. If you have a lossy network and you're working with Akka and you're going to send messages, it would be really handy to know that as long as it gets there at least once, like you can do your thing, and that's what idempotency is all about. So people talk a lot about semigroups, monoids. I wish everyone would also, like, if you hadn't heard of semilattices before, take those home and think, oh, that might be useful for something I'm doing. So these types all made it into something that wound up being called Cat's kernel. And Cat's kernel is a part of Cats that Cats itself depends on. So if you use Cat's monoid, it's actually just a type def of Cat's kernel, which came from this whole effort. And that's pretty cool. There's like Mima has locked that down pretty much, and that one's been pretty stable. So that one doesn't move. And so that's the one that we've kind of now the algebra project depends on that. So we're nice guys. We know when we've lost. So Cats is like, people like Cats. That's cool. So now the algebra project depends on Cat's kernel. Cats, there's more to algebra than just monoids, right? In fact, if everyone, you're into cryptography or coding theory, you might be into fields. These are great. They have a bunch of other properties. So with the ring-like and lattice-like kind of, they usually have two operations. These don't come up so much in category theory. So Cats doesn't have so much of a use case for this that I know of. Maybe some people who are better experts at category theory can tell me wrong. But we have addition, we have multiplication. That's what like kind of the ring world is all about. Not the science fiction book. So there's these cute things, RNG. It's a ring without an identity element. You get it, Rig is a ring that doesn't have the subtraction, no negation, So there we go. So there we have these nice tables, and these are all in algebra. So now algebra depends on Cat's kernel, and the algebra projects here are all these other types. These are really getting kind of like specialized. Like if you think of lattices, they have a lot of analogous structures. Like if we think of the actual type lattices that come up, you've probably seen tops and bottoms, and they have upper bounds and lower bounds. Those can be related to meet and join lattices that you might have some use cases for. But now there are PRs, finally, years later, against both Spire and Algebird to replace all their type classes with these. They will be merged very shortly. Eric and I now work at the same company, so we're more motivated to unify these things. And at that point, when you say monoid in any of these projects, CATS, Algebird, Spire, Algebra, you're talking about the same type. So if you want to go and use so what can you wind up doing then? So like Spire, what's the difference? So you might think they're actually really well factored. So Spire is really about numerics, really fancy, awesome numerics. Like there's really almost no question where you say, should I be using Spire or Algebird? Because they're covering totally different domains. So it's really great that they can use the same type classes and work together. So Spire can give you an awesome rational type that is really efficient. It's really fast. Eric writes amazingly fast code, really high performance, but with some beautiful abstractions. Tom Switzer, who also works with us now at Stripe, wrote this awesome computable real implementation. So real numbers, we normally think of them as being like, you can't they're like doubles, right? But many reals can be computed, like square root of 2. I can't write down all of square root of 2, but I can give you an algorithm that would produce the nth bit of the square root of 2. Likewise for pi, right? So they have some awesome classes to deal with these kinds of things. Polynomials form a field even. So you can divide polynomials, you can multiply polynomials, really cool stuff. That comes up in coding theory, actually. On the other hand, Algebird, as we've talked about before, it's more about these big approximation data structures. So that's kind of the state of affairs. So the take-home message that I want you to know about is that one thing is it's a cool abstraction that I don't see a lot. Aggregators, that kind of applicative functor of like a semigroup with a map, really, really useful. If you're into counting, analytics, building machine learning features, you should build reusable libraries of this or use Algebird. I would recommend it. Algebird has many well-tested, they're correct. Someone got on my case, I don't know if they're here, about like the Bloom filter being too slow in Algebird. So here's the dirty secret. We actually never used Bloom filters at Twitter, and that was a contribution, and I'm a nice guy, and I take contributions. So like, whatever, man. But so number 3. We now, very shortly, I promise you, before the end of the year, there will be one monoid to rule them all, one ring to bind us, right? On CATS, Algebird, and Spire. So that's it. There's Algebird. I'm at Stripe. There's my email address. That's me on Twitter. Follow me on Twitter. Always in a competition with Peter Seibel to see who can have the most followers. He's doing abuse at Twitter now, so he's like pulled ahead of me because for obvious reasons. And and Stripe is always hiring. And look at all these fun people you could be working with. There's Eric, there's Sam Ritchie, there's Tom Switzer, there's Avi Bryant, there's myself. Look at all those Scala projects. So come talk to me. That's my whole talk.
There is time. Do you want to take some
Sure,
questions?
yeah. I'm happy to take questions. I think we've got some time. Started to speed up there and get a little looser at the end, so. Yes?
What would you suggest for complex numbers?
So the question was, what would I suggest using for complex numbers? Spire has awesome complex numbers. They have quaternions. You can do complex numbers over integers, complex numbers over doubles, complex numbers over computable reals. So it's got some really cool complex number handling. Yeah. Next question. All right. Thank you for coming to my talk.